Unit 2 Chemistry, Chapter 2, Part 2. More trends in the periodic table. So electron configuration next. The electron configuration is how many shells there are, how many are in the outer shell, what subshells are filled, and so on. That is what determines where they are on the periodic table. I mean, when Mendeleev put it together, he was basing it on their properties and basing it on their mass, but we actually now know that those properties are determined by their electron configuration, so things like their reactivity. Okay, so if they're in group 1, they've got 1 outer shell electron. Group 2, 2 outer shell electrons. In both cases, the last electron goes into an S subshell. So we call groups 1 and 2 the S block. Okay. In groups 3 to 12, we're filling a D subshell, so that's our D block, otherwise known as our transition metals. For all of those, there are 2 electrons in the outer shell. Apart from those chromium and copper exceptions that you've already learnt about, where to increase stability, they've actually only got 1 in the outer shell. Groups 13 to 18, we've got a P subshell, so this is our P block. The number of electrons in the outer shell is 10 minus the group number. Okay, that's the group number minus 10. Okay, so 13 minus 10 gives you 3, so there's 3 in the outer shell. My apologies for that error, it is group number minus 10. And the actinoids and the lanthanoids, down the bottom, okay, they fill an F subshell last. Okay, so that is known as our F block. Which group they are in, or which is determined by the number of electrons in the outer shell. Which period they are in is determined by the number of electron shells. So if they're in period 1, they've got just 1 shell. Period 2, 2 shells. Period 3, 3 shells. Nice and simple. Okay, so S block, D block, P block, and F block. Okay, and you can even say that here, for instance, they've all got S2 and then P1. Electronegativity. So the electronegativity is what we call the electron attracting power, how strongly it can grab onto electrons. Might be its electrons, might be the electrons it's grabbing from somewhere else. Depends on 2 things. It depends on the core charge and the atomic radius, which of course are linked together anyway. Okay? If the atomic radius is smaller, then it's going to have a big electronegativity, because the outer shell is going to be closer to the nucleus, so those forces of attraction are acting over a smaller distance and therefore are going to be more powerful. Okay? As we go down the group and we are adding shells and we are increasing that atomic radius, that means that they're getting further away, so our electronegativity is going to be decreasing. So if we go across a period, the atomic radius is going down, so the electronegativity is going up. As we go down a group, the atomic radius is going up, so the electronegativity is going down. So because of that, top right is where you find your most electronegative elements. Nitrogen, oxygen, fluorine, they're the top 3. The noble gases, we don't actually measure their electronegativity, because we measure electronegativity when they react, and noble gases, of course, don't react. Now, linked to electronegativity is ionization energy. So that is how much energy it takes to remove an electron. First ionization energy specifically, how much energy, the minimum amount of energy needed to remove the first electron. Okay, so if the electronegativity is bigger, yeah, because the core charge is bigger and the atomic radius is smaller, then it's going to be much harder. Okay, so as the electronegativity increases, so does the first ionization energy. So as we go across a group, that's what we see. As we go down a period, we see the electronegativity decreases, and so does the first ionization energy. Okay, so these are our first ionization energies. Yeah, these ones, lithium for instance, big atomic radius, so further away, so relatively easy to get rid of that first electron. As we go across the group, we see that that is increasing. Now this is important. Remember we said this was about trend. So we'll see a couple here that kind of buck the trend a bit. Beryllium's higher than boron. Nitrogen's higher than oxygen. You're going to see anomalies, but we could do a line of best fit and we're clearly seeing overall an increase. Okay? And the same thing happens in both of them, in this period as well, period 3.